Hello there, and welcome. This video is on section 5.3, where we're going to be explaining the meaning of this integral notation, and we're going to be explaining some connections between that and the notation we learned in the last video. So this is a classic example where mathematicians are just confusing and unnecessarily so. They are using the same kind of notation to mean two completely different things, and yet they're kind of calling them both the same thing. Let me be more specific. So the notation we're going to be talking about today is this S notation with this f of x and a dx, and it does mean multiplication, f of x times dx. Although, once again, math people don't write the time symbol in there because they just don't like doing that. That's the notation. And this is called integral notation. And if you're saying, now hold on a second, we did integral notation last time with the s and the f of x times dx, you may remember one other detail. And the other detail was the fact that it had some x values here. So x equals a, x equals b. And of course, we had f of x dx. These are both called integral notation. If you want to know an adjective, this one is called a definite integral, and this one's called an indefinite integral. Let me move me over there. Indefinite. I don't know if those words really help at all. And math people typically just call them integrals. And they really, really, really mean different things. So this guy, if you remember, meant the area. It's the signed area between the function and the x-axis on the interval from x equals a to x equals b. This new guy right here, this fx dx with no x equals a, x equals b, it doesn't have anything to do with area. This thing is called the antiderivative. So right here, this fx dx thing, this integral, indefinite integral, if you want to call it that, represents the antiderivative of the function fx. In other words, whatever this answer is, if I took the derivative of this thing, I get back the original function. And we did do antiderivatives before. You may remember I gave you like some function. It was like x squared or something. And I asked you, or I gave you a derivative function, excuse me, and I asked you if you could go backwards and find the original function, what would it be? And we did a few practice problems and things like that. This one ends up being 1/3 x cubed plus c. And the way we knew that was the antiderivative, that was the original function, is because if we differentiate this answer that we get, if we differentiate the 1/3 x cubed plus c, we get back to the original x squared type thing. So the idea here is this integral notation without the a and the b thing just represents the going backwards, the antiderivative of whatever function is in there. And the way the mathematicians communicate that is whatever answer you would have gotten for that antiderivative, if you differentiate it, you get back to the original function. So it looks a little confusing with all the parentheses and all the calculus notation. Let me zoom in a little bit. But that's all they're trying to say, right? This new thing, this antiderivative integral thing, which I'll just put a circle around right here. The antiderivative just means that when you differentiate it, you get back to the original function. So these are two very, very different things. Area versus antiderivative. And so the reason why they use the same notation, even the same wording, is because it was discovered, after a couple thousand years of people doing calculus, that you could calculate the exact area using the antiderivative, which is quite remarkable. No one really had a clue that this was possible. These were taught as completely separate ideas, antiderivatives and areas, until Leibniz came around, a few other mathematicians, and they said, hey, look at this. We can use the antiderivative to calculate the area. And that is called the fundamental theorem of calculus. And I'll show you what that looks like right down here. It basically says that you can calculate the exact area by using the antiderivative. And that's why they end up using the same notation and the same language, because really they're completely connected. We don't really see the connection yet, but they are fundamentally connected through this formula here. I'm not going to prove the fundamental theorem of calculus for you. There's a nice proof in the book, and there's lots of proofs online. And of course, I can show you one if you want to log into my Zoom hours, and I'll go through it with you as well. But basically, if you understand how the rate of a function, the bigger it goes up, the bigger the area is going to be, right? So the rate of a function is connected to the area. The faster it goes up, the more area you get, right? The slower it goes up, the less area you get, right? So there's a fundamental connection between our rate, our derivatives, and the area. All right, so I'll just leave that intuition as it stands and talk about what the fundamental theorem of calculus says. So this is the version of the fundamental theorem of calculus that I write down. It can be written in many different ways. And so I write it this way. So what does this big old mess mean? What's going on here? So I'm going to write this out, and I'm going to explain this piece by piece. And hopefully, after my explanation, you'll see that this is really not as complicated as it looks. So here on the left-hand side, that is the integral notation with the a and the b there. So this is just the area. This is the area between f of x and the x-axis. That was the first integral notation we learned. All right, so what's on the right-hand side? This right here is the antiderivative. Like my example was, like if I was given the function x squared, then the antiderivative would be 1/3 x cubed plus c. So that's the antiderivative going backwards. And you may also remember that I introduced these line things. So maybe some people had seen them before, but a lot of Calc 1 students haven't seen these lines. This line just means evaluate or plug in at that value, right? So we, found the value, we plug in b, which is our right-hand endpoint, and you get a number, right? So you get some antiderivative function, you plug in the right-hand endpoint, and you get an answer. And then over here, we do the exact same antiderivative. So this is the same antiderivative both times, except that we're going to be plugging in the left-hand endpoint, x equals a. So what you end up doing is you end up finding the antiderivative of our function, plugging in the left-hand endpoint, the right-hand endpoint, subtracting those two, and that gives you the area. So the area is going to be calculated using antiderivative by plugging in the two endpoints, a and b, and subtracting. And that is called the fundamental theorem of calculus. Let me show you how that works. Let me show you a couple of examples of using this theorem to find an integral, and in fact the exact area. All right, so my first example right here is example A, and it says use the FTC, fundamental theorem of calculus, to find this integral from 1 to 4 of 2x plus 3 times dx. So we know this is the function inside, 2x plus 3. So we have to do the antiderivative. And oops, I dyslexed that. Antiderivative. So you got to find the antiderivative to use this formula. Now, you may remember this from our previous work. If they don't call f prime originally, then we usually call the antiderivative capital F, just so we can remind ourselves that, we did go, in the opposite of the derivative direction. So now you have to think about how do we antidifferentiate 2x plus 3. You've been practicing some of these. So let's go in chapter 4, we practiced some of these. So let's go ahead and remind ourselves how to find the antiderivative of this thing. The antiderivative of 2x is x squared. The antiderivative of 3 is 3x. And we do need our plus c for doing antiderivatives. So that's our antiderivative. We're going to take our antiderivative and we're going to evaluate it at the two endpoints, the right-hand endpoint first, the left-hand endpoint second, and subtract those two. So we're going to find the value of this thing, the value of the derivative at 4, right? And we're going to subtract the value of this antiderivative at 1. Now, math people don't write f4 minus f1. What they'll say is that we're going to calculate the x squared plus 3x plus c at x equals 4 minus the x squared plus 3x plus c at x equals 1, right? So they're going to use that line to represent the fact that we're taking the thing and evaluating. But honestly, it's the same thing as just doing F4 minus F3. All we're doing is plugging in 4 and plugging in 3, right? So here we take this thing here and we plug in 4. So that would give us 4 squared plus 3 times 4 plus C. And then we subtract and we plug in 1. So that's 1 squared plus 3 times 1 plus C. I have a little bit of space there. Let's see if I can pull the screen over. There we go. So just make that a little more obvious what I'm writing down here. Plus C. So in this first thing, we have 16 plus 12 plus C. 16 plus 12 is 28 plus C. And then we're going to subtract off 1 squared is 1, 3 times 1 is 3, so this is 4 plus C. You may be seeing that we have plus C and a minus C, so those C's are going to go away. So we get 28 plus C minus 4 minus C. And so you have plus C and minus C, which is 0. This happens every time, right? So, since we're calculating the value at the two endpoints and subtracting, we're always going to get a plus C and a minus C. Plus C for the the right hand endpoint and minus C for the left hand endpoint. So a lot of times people just don't even write the C anymore, right? When you're doing an area calculation using the fundamental theory of calculus, and you know that the plus C and the minus C are just going to end up being 0 anyway, you could just not even write the C. The problem is a lot of calculus 1 students forget it a lot, even when it needs to be there. So you might want to write it just so that you don't forget it in the times you need it. Anyway, to finish up this problem, 28 minus 4 is 24. So 24 is the area between this function 2x plus 3 and the x-axis from x equals 1 to x equals 4. And we did that using the fundamental theorem of calculus. All right, so hopefully that explanation works well for you. A couple little things. We actually did this problem previously using geometry because it ended up being a triangle. So you can go back and look at the notes and see if you got 24. I think we did when we used geometry, because this ended up being just a straight line, and we could use just like an area of a triangle to find the area formula. The other thing is that the way mathematicians write this out is, again, they just love being confusing. They combine these things into one thing. So they combine the evaluated at 4 minus evaluated at 1. They combine it into one symbol. So let me show you what that looks like, just so you can see it. Because when you watch the videos or read the book and stuff like that, you'll see something that looks a little bit different, and I just don't want you to be blindsided saying, wait, that looks different than Jim's video. So here's how it goes. We have the integral from 1 to 4 of 2x plus 3 times dx. We know the antiderivative of 2x plus 3 is going to be x squared plus 3x. And if you want to write the plus c in there, I'm going to be writing the plus c. And then they say this funny bracket with these little extra wings on them. And then they'll say from x equals 1, that's the lower limit, to x equals 4. So again, this is just notation. All they're saying is plug in 4, plug in 1, subtract the numbers, and get your area. But it's, layers of confusing notation that I'm just trying to help you, get through, so that you don't get a little frustrated when you're like, what does all this mean? It's just math people trying to be cheeky about writing their calculations in the most succinct way possible. So just again, the fundamental theory of calculus, find the antiderivative, plug in the right-hand endpoint, plug in the left-hand endpoint, subtract, you get your area. All right, let's do 2 more examples, and then we'll be done with this video. So my second example here is to use the fundamental theory of calculus to find this creature. If you haven't already thought about pausing the video to give one a try, this might be a good one to do so. And then I will show you my solution. All right, so did you pause yet? Or do you not want to pause? All right, well, hopefully you're coming back now and you have your answer, and you are saying, okay, what did you get, Jim? I'm going to write out the steps. So I have to find the antiderivative of this function. This is my function 2 minus sine x. That's my f of x thing. So I have to find the antiderivative. I'm pretty good doing antiderivatives, being a math teacher and all. So the antiderivative of 2 is 2x. The antiderivative of minus sign, or the antiderivative of sine, is minus cosine. So the antiderivative of minus sign is plus cosine. And I do get my plus c for my integration. And then I'm going to be evaluating this at the two endpoints. I'm going to be using this, funny notation. So I'm going to evaluate it at x equals 0 and x equals pi. Those are the two endpoints. The bigger endpoint goes on the top, and that's the one we do first. So we're going to plug in pi. So that's going to be 2 pi plus cosine pi plus c. So that is when I plugged in the x equals pi. And then I'm going to subtract when I plug in x equals 0. So x equals 0 is going to be 2 times 0 plus cosine of 0 plus c. All right, I didn't leave myself enough room there, so let me just fix that. Cosine of 0 plus c. And then we just have to do the math here, and we get the value of the area, or the value of this integral. All right, so what do I get here? I get 2 pi. Cosine pi is the x value at an angle of pi radians. So if I think of a unit circle and I go pi radians, I end up on the negative side of the x-axis with an x value of -1. And of course, I get my plus c. And over here, I'm going to be, I guess I'll still write this in parentheses. Over here, I'm going to be getting 2 times 0, which is still 0. Cosine 0 means the x value at 0 radians. So you're on the positive side of the x-axis. The x value there is 1, and we get a plus c. All right, those are supposed to be in green. Let me try to color coordinate this. All right, so let's just remove these parentheses and get our final answer. So we get 2 pi -1 plus c, and then we get minus stuff. We get -0, which is just nothing, -1, and we get minus c. And once again, of course, we have a plus c and a minus c, which is what I was referring to before, is people just stop writing the plus c a lot when they're doing these fundamental theorem calculus calculations, because they end up realizing, oh, the c's are going to cancel. Anyway, I continue to write them just to demonstrate that they don't magically disappear. They just add a 0 each time. So my final answer is 2 pi -2, -1 -1 is -2. So right there, that is the area between the function 2 minus sine x and the x-axis from x equals 0 to x equals pi. We did that using the fundamental theorem calculus. Very, very important theorem. You might even call it fundamental. All right, my last example here is on the next page. We're going to calculate this thing right here. So once again, this is an integral with numbers, definite integral, if you want to call it that. And so we need to find the area. Now that is a pretty complicated looking function. We're going to use the fundamental theorem calculus whenever we can. So we'd have to find the antiderivative of this creature in order to use the fundamental theorem calculus. If you can't find the antiderivative, you can't use the fundamental theorem calculus, because you have to plug in numbers to the antiderivative in order to use the formula. So how do we do this? Remember that we can use algebra to simplify things, and that will help us find the antiderivative. Antiderivative is hard to find. Antiderivatives are a thinking backwards problem. What would the original function be, so that if I differentiate, I get to this new thing, right? So it's a thinking backwards. So you're going to be learning some sophisticated ways to simplify these functions so that we can figure out what the antiderivative is. But we can always use our basic algebra too. So we're going to use our basic algebra for this one, and later on in chapter 5, I'll show you something where it's a pretty sophisticated way of simplifying functions so that it'd be easier to find the antiderivative. All right, with all that preamble and the spoken about doing the problem, let's actually do the problem. So I'm just going to write the same integral here. You can write the x equals 1 and x equals 2 if you want. Math people aren't going to write them because they're like, oh, why do I write those? It's too much to write. So maybe I'll leave it off this time. I'll pretend to be a mathematician. And the function 3x to the fourth minus x over x squared may be simplified by using the distributive property. Distributive property works for multiplication or division. This is a division problem. So we're going to get 3x to the fourth over x squared minus x over x squared, and that's all times dx. So we have our integral from 1 to 2. 3x to the fourth over x squared would just be 3x squared. And x over x squared is minus 1 over x. And that's times dx. And the antiderivative of 3x squared, we can do. That's one of the ones where you can think backwards, and you've actually probably done before. And we can also antidifferentiate 1x. I know you've done that before. We did it several times in our chapter 4 homework. So we can now recognize the antiderivatives for these with a little bit of thought, maybe trial and error. So the antiderivative 3x squared is actually x cubed. Think about differentiating x cubed, you get 3x squared. And the antiderivative of minus 1 over x is minus ln of x. The derivative of ln x is 1 over x. So the antiderivative of 1 over x is ln x. And then we get our plus c. And we're going to evaluate this at the two endpoints at x equals 1 and at x equals 2. So I'm just going to start plugging in numbers. So I'm going to get something minus something. And when I plug in the higher value, I get 2 cubed minus ln of 2 plus c. And I plug in 1, I get 1 cubed minus ln of 1 plus c. 2 cubed is 8, so 8 minus ln of 2 plus c. And then I get a minus, so minus 1 cubed is 1, minus a minus ln of 1 is plus ln 1, but ln of 1 is 0, so it's just plus 0, and they get a minus c, which of course classically we get our plus c and our minus c, and so we get 8 minus ln of 2 minus 1. I can combine the numbers together, 8 and 1, so my grand total, if I can write it over here maybe, is 7 minus ln of 2. And that is the area between this function, this crazy function, and the x-axis from x equals 1 to x equals 2. And that, my friends, was what this notation means and how to use the fundamental theorem of calculus to compute an area using our new antiderivative integral notation. So hopefully all this kind of made sense, but please reach out if you have any questions or if you want some more examples of how to use a fundamental theorem of calculus, how to use antiderivatives to calculate the exact value of the area, right? That's what the fundamental theorem of calculus is. You're using antiderivatives, plugging in some numbers, and that will give you the exact area between the function and the curve. All right, well, hopefully this was helpful, and hopefully you enjoy your day.